Hello and welcome to our presentation about finding the needle in the haystack with Elastic using AIOps. Today we will dive into challenges faced by organizations while having to pinpoint the source of problems in a timely manner. I'm Hugo and I'm a software engineer working at the competitive intelligence team here at Elastic. So it's estimated that we generate approximately 10 terabytes of data per second these days. And you might think this data is mostly TikTok videos, but not really. Think about every online interaction you have throughout your day from the multiple devices you use. The reality, which most people outside of IT don't quite realize, is that you leave a trail in the multiple systems you interact with, directly and indirectly. This trail is composed of logs, metrics, and application traces that are constantly being generated. And systems get more fragmented over time as well, more specialized, which increases the amount of data generated by them. Anyone who ever coded or managed microservices knows what I'm talking about. And I know you probably know all this already, and you know that especially if you are the main persona of this talk today, which is the site reliability engineer. This role is responsible for keeping systems up and running, detect problems earlier, and basically keeping customers happy, whomever this customer is, internal or external. However, problems always happen, and when they happen, the SRE's job is to find the culprit as fast as possible, right? Finding the origin or source of a problem is the first step for having it solved, correct? And what does the SREs have at their disposal for performing this analysis? Well, we have the umbrella term of observability data here that refers to three things. Metrics, which will tell them how much, like how much memory is used, how many users are active, right? Logs that will tell them what the systems we're doing. Sometimes who as well. What user, what system, in form of unstructured data that needs to be interpreted or parsed, as we say, and traces that will tell them how long each interaction or transaction took inside one or multiple systems. We call that distributed tracing, and it's very useful for having a perspective from inside the systems, right? We could also add here profiling as well, which would be much more fine-grained from a resource usage perspective. And of course, the when, or the temporal dimension, is always present in all those things. Otherwise, we could not do correlation, which is essential for this, for finding the root cause. And what are the challenges for doing root cause analysis? Maybe the top three are data volume. We need to collect observability data for doing correlation as fast as possible. Second is human error. And it's simply not feasible to inspect all this data fast enough. So it's easy to overlook problems. So machine learning can help here. And the application of machine learning is known as AIOps, as you probably know. The last one is data silos. Since the observability data is often stored closer, quote unquote, to the systems that are producing it, which means they are isolated from other systems, right? Which prevents, obviously, fast access and correlation of this data. I'm going to focus today on those first two. Okay, so what do we have to help you perform root cause analysis in Elastic? I'm going to demonstrate three things. First one is explanation of log spikes. So I'm seeing an increase in log messages. Are they related to a specific field in my data? A specific user or whatever? Second is latency and failed transactions correlation. Can we identify the slowest transactions from the rest? What do they have in common? A version, a URL, a microservice? What is it, right? And the same for failed transactions. And the last one is anomaly detection. And I'm going to do that on top of business metrics that are derived from log lines, actually. Our systems might not be tracking metrics that are important to the business, but we can derive those metrics from the log lines. For instance, if I have a log line that says payment processed with Visa card or whatever, right? I can transform that into a metric, and Elastic will establish what are the normal thresholds for that metric, what's the minimum and maximum, and then you can detect anomalies on this time series that was derived from just messages from the system. That is especially important to verify that whatever issue that caused this important metric to go down have now been resolved, as the metrics back to normal levels, whatever normal is, right? You don't need to specify that yourself. That's automatically derived by from the time series. Okay, so the demo, we're going to use the same demo from the Elastic AIOps Essentials. That's a series that's published. We'll use 20 microservices from the OpenTelemetry demo. Actually, we have a front end, and this front end will obviously generate several events. Those events propagate through this 20 microservices that we have in there. This is all deployed in Kubernetes in a scalable environment, but none of this stuff matter, because I could have collected logs from virtual machines, right? Not necessarily from microservices. It's just that this demo is really handy, very useful to get it deployed if you want to try it by yourself. Okay, so let's jump to the best part of this talk, in which we get to break things on purpose. So I'm going to disrupt one of the services that are in there on purpose, right? I'm getting the currency service, which is a very simple microservice in this demo. This currency service just basically does converts the price of products whenever you put something in your cart. You put a product in your cart, you go to the checkout, if I'm not mistaken, and then it converts the prices of the products. It's very simple. However, this microservice exposes a port, which is 8080. I'm changing it to 8081. Very simple mistake, actually, but the service is basically, it's going to stop responding. And I'm going to increment the version of that, of all the services actually, as they are progressing like together. So can Elastic catch this error? Elastic can catch this error in several different ways. Let's switch to my Elastic Cloud instance. Okay, so let me first show you an overview of the services. If I go to APM, collecting everything in here, all the microservices are there. This is the last 24 hours. Let's just switch to the last hour. And yeah, the change I made to the currency service is right here. So shipping service stopped working, and currency service as well. The throughput went down, right? And the failed transaction rate went up right here. Interesting. If I click one of the services, so everything starts in the front end. Let me just click on the front end in there. You see that there's a version tagged in there, version 1.4, right? And that's exactly when I started, when I published that version, right there, right? And we have actually the message in here, fail to prepare or fail to convert price, right? But I'm here in the front and I know that I have disrupted that service. Can we catch that error, this thing right here, automatically? Let's switch to machine learning. And we have AIOps labs right here. Explain log rate spikes. Let's switch to logs. And I'm interested in a specific, I'm interested in when things go wrong. So basically they are tagged APM error. They're coming from the APM, they are an error. I can click any spike in here, just click this, right? And Elastic is going to compare to the previous events. We are going to find values in there that are highly correlated to that spike. So that values that were not there before, basically. If you click on group results will show us that we have several types, several errors related to the same thing, fail to convert price, and they all appear in the spike. You see that they are painted in white, in yellow in there, right? There will be also the version in there, right? Just expand this here. Probably version will be in here. Service.version 1.4, right? So it's really useful to explain spikes. If I just click another spike, I'm just explaining this one compared to the other log lines, right? See that I'm getting probably, can we group the results? Okay. Inactive RPC errors. The recommendation services was failing at this point, right? And you'll see that it will point to different errors in there if they are correlated to the log messages, to the events. And you can drill down into those logs. If you just click and discover, it will take you to the raw log messages in there, right? It will fill the search bar for you. So that's one way you can automatically catch those errors by explaining log spikes. Really useful. Let's go back. Now we have the second way we can catch the same error is by using the latency and failed transactions correlation. So we are using APM, right? So we have distributed tracing. Can that error or the propagation of that error show up in Elastic? So can we see from all the transactions that are failing or that are slow? Obviously, if I cannot reach a service, it will time out, right? So whatever service is consuming information from that microservice or communicating to that microservice will time out. So the transaction will be slower. So do we have anything to point us to the root cause of those failed or slow transactions? Let's go back to Elastic. If I come here on APM, let's get from the front end, right, where everything starts. So you see I've had two versions in here, 1.3, 1.4 is the latest one, the fail one, the failing one. That's the 1.4. Let's put the last hour in there. Yeah, so this the 1.4 in there. It's in there. Good. We have the transactions in there. We have a post and a get. The post is the one that are actually doing checkouts and everything, not the get ones. And I see that from that point, 15, right? 15 past 2 p.m. We have a failed transactions of about 24%, 26%. You see, those are this is the percentage of the transactions that are actually touching that microservice. And we have the distributed tracing in here, right? And I can inspect all the transactions that are actually touching the several microservices in there, right? And they are going through multiple microservices. In this case, front end and card service. See if I can pick one that goes longer, we'll pass to different microservices. Yeah, this one, for instance. So this transaction right here have front end, checkout, cart service, and product catalog service. The checkout is failing, right? So my main transaction in the front end is failing. This transaction goes to the checkout go to cart service, and you guessed it, that checkout service, it's touching the currency service, which is failing because we made them fail, right? You can see in here. To have an automatic way of looking into that, failed transaction correlations right here will show us that the service version 1.4 is highly correlated. You see in here, service version 1.4 is highly correlated to the failing transactions. And I can inspect, if I just filter service version 1.4 right here, right? It will show me the reason why it's failing, right? It's actually the checkout microservice is failing. Let's clear this filter out. Failed transaction correlation, it's right there. What about latency? We have clearly transactions that are taking 20 seconds. As I said, they're probably timing out. Can those be explained automatically? They can, right? They all touch the checkout. They are all 500, obviously, and some of them are using the API checkout, API/checkout. So probably the checkout microservices. And the last thing, it's anomaly detection. So anomaly detection, as I said, we can derive business metrics from the logs themselves, right? Even if my developers are not actually tracking that specific metric, I can derive that, create a custom metric if you want, from the log lines, and track that and establish the thresholds for that. Let's see how that works. Okay, so we have the logs from the microservices in there, and I found one that's particularly interesting, which is from the cart service. The service is producing logs that would say product ID, then an ID, and then a quantity. This is a type of metric that, similar to metrics that I have seen in the field, you have an ID and then you have a number in there. However, you want to extract that. This is inside a piece of unstructured text, right? You can create a runtime field and parse that message from that specific log line, from that specific service, and then you will have that ID and quantity exported, so to speak, as a metric in there, right? And so it's an attribute now of that log line. And now we can do some interesting things with that. We can, since we have the metric, then we can now analyze it for anomalies. So let's select a multi-metric job in our machine learning module. And then we are going to select the metric that we have just derived, that custom metric that we just derived from the log lines, called cart product quantity. So this is that's a metric for all the products. We can then split per product, and then Elastic is going to create one statistical model per product ID, and then we can basically what this is going to do is that this is going to compare the behavior of every product with its past behavior, basically. So we're going to create independent metrics from that, independent jobs from those metrics. And then we can see that something happened in there. We see the anomalies in they are displayed in there. You see the metric for this specific product was around 4. The normal was around 4, and we got like 2, something like that. And we can see that blue, light blue shade behind the actual metric. That's what the model is expecting for that specific product. Yes, we can obviously use those visualizations on top of inside a dashboard that will in turn correlate that metric with others from APM, for instance. So you can correlate if there's something going on, for instance, that in that service, in that specific service, something started to behave differently, you will immediately notice, and that will help you find the root cause of issues much faster. Okay, so hope you have learned something new today, and see you next time. Thank you very much.